If you look really closely at this waveform, it deviates from the ideal a bit, and we'll have to look at a little bit finer grained in time to really see that. So notice as I change the time base to 5 microseconds per division, you can see the waveform doesn't quite make an instantaneous change and then start to decay down. It kind of has this, kind of exponential type of wavefront, and then it starts to decay back down. So what's really going on? I mean, we expect to see something like this. If you remember, when you're looking at the transient response of an RL circuit, just draw the circuit really quick right there for R and RL. We look at the response to a step function. We're measuring the voltage on the output, VL right there. And our theory said that when the step function happens, time t plus 0, see an instantaneous spike in the voltage across the inductor, and then it's going to exponentially decay back down to 0 again. But what we were actually seeing is it was kind of rounded, and then it started to exponentially decay. Like it didn't quite make it up, and we were missing the part right here that I'm filling in with the pen, like this piece right here. That's just gone. So what actually happens is that an inductor is not it's a non-ideal device, much more so than the capacitor at these frequencies. And there's actually capacitance in the inductor, which is just a function of the turns of wire being close to each other. So the circuit really looks somewhat like this. Let's get that VL out of there to make it a little bit more clear, where you have an inductor and a capacitor in parallel. And we could do a demo of that. So we go back over to our setup over here. We have our waveform and then our breadboard in view. And I'm going to take this capacitor right here. It's a 100 picofarad capacitor. And I'm going to attach it across the leads of the inductor. First I'll turn on the scope again. It looks like we need a little bit more intensity on that scope screen. To adjust the intensity of the waveform on the screen, push this button down here, turn it up, so now you should be able to see it much better on your computer screens. Okay, so now we can see that. Pan down a little bit. I'm going to insert the capacitor across the inductor, so it's literally connecting it in parallel to the inductor. And you're seeing a bunch of noise right there, so that noise is all just coming from my finger. You can see when I inserted the capacitor, it got even more rounded. I could pop it out of the circuit, get square, stick it back in, it gets more rounded. So this is like adding a lot more parasitic capacitance, like an unreasonable amount to the inductor, and really making it behave non-ideal. But when we remove it from the circuit, you could still see that there's that kind of exponential rising edge right here, which resembles more of an RC circuit. And that's coming from that parasitic C that is in the non-ideal model. So there was another thing that we also saw. If you recall, when we were looking at more of the waveform, more longer time history of it. So down on the output, you could see there's a step up and a step down and a step up and a step down. I could make that a little larger by changing the time base on the oscilloscope. So now I'm on 20 millivolts per division, and we could see when we make the positive transition on the function generator, right, we step up by about 1 division, which is 20 millivolts. When we make the negative, we step down. So when we put the 1 volt signal on the inductor, even long after the exponential decay died out, which is just that little line right there, it's sitting at this DC value, that's 20 millivolts above ground. So if we go back to our inductor one more time, so there's another thing you could model in a simple inductor as a non-ideal thing, and that's there's resistance in the winding. Like we know an inductor is a big coil of wire, and that wire has a finite resistance. Draw a better resistor. So there's a resistor that connects to the inductor right there. So that's another non-ideal element. So the resistor and the capacitor are both things that are non-ideal in the inductor, and those prevent it from behaving exactly as we'd expect it to.